we've looked at the most popular, most common types of web app attacks. Let's look at some others. So of course, you can do a denial of service against a web app itself. You could overload server resources by sending hundreds of requests or thousands of requests to a web app. This sort of app-level attack will simulate requests from legitimate clients, so it's undetectable. It looks like just suddenly the site is really popular. Vulnerable apps could be ones that have poor validation of data, flaws in implementation. They don't have a good expectation of the amount of load of usage, or there are bottlenecks in the environment itself, like not enough CPU, not enough RAM, not enough disk. So we could do denial of service against the web app itself, or some of the underlying hardware, or the operating system, or the server service. We can do buffer overflow attacks, and buffer overflows are basically where there's no input validation, there's nothing to stop us from putting in more, and overflowing the pre-allocated block of memory for the input buffer. That's why it's called a buffer overflow, which means that the malicious code is going to spill out past those memory boundaries. So when an application starts, it wants two things. It wants threads, which is the smallest unit of execution of code, to run on the CPU. And it also wants some memory to do its thing, to load itself, to load documents, and to have input and output buffers. So we could just take advantage of an app that is taking input, and it has like this much memory space available to hold that input. If there's nothing stopping us from keep on overflowing the cup, so to speak, pretty soon the code is going to spill out past the memory buffer into surrounding memory addresses. And with any luck, one of them will execute the code in the privilege level of the service that owns that whole thing. So hopefully at system level, right? So that's a buffer overflow. A heap overflow is basically a buffer overflow, but it is the buffer is allocated on the fly, as opposed to set up when the app first launches. So we could do a buffer overflow attack against an app or against a service that runs on the web server. So the app is going to, not meaning to, but because of unstopped user input, write more data to a block of memory than the block of memory can hold. And this allows us to change the address space of target processes, and we can do direct program execution in memory locations that contain our malicious code where we shouldn't be. As we've said before, we could poison session tokens and cookies. So we know that cookies and tokens are required to maintain the session state because of the stateless version of HTTP. So poisoning means we're altering the cookie content. We're permitting the injection of malicious content. This alters the user's experience. It gathers sensitive information. It rewrites sensitive information in the session. Session fixation, like we said, we're going to go ahead and get a legitimate session ID, but then we'll trick the user's browser into using that which we are now already in control of. So they're going to use that session ID and log in, and now we've got the same session ID and we're already logged in. Thank you very much. CAPTCHA attacks. So, a CAPTCHA, of course, is something that is kind of a nuisance, but it's meant to prove that it's a human looking at the page, not an automated process. And so, like, you've probably seen CAPTCHAs where you'll see all these squares of pictures. Click every one that has a bus, or every one that has a storefront, or every one that has a street sign. Or type in the letters and numbers that you see. Or just go ahead and click I'm not a robot, and it tracks the way you move your mouse and says, oh, that's the way a human would do it. So these are all examples of CAPTCHAs. It's meant to stop automated malicious processes from simulating human user activity. However, there are indeed attacks against CAPTCHAs as well, which if we could successfully attack the CAPTCHA, we could get around that control. So CAPTCHAs are supposed to not allow automated software to perform actions on a system. The goal is to ensure that it's actually human. But there are CAPTCHA vulnerabilities to compromise web apps. So type of CAPTCHA attacks, breaching the client-side trust, attacking the CAPTCHA image, manipulating how the server implements it. Maybe there is insufficient protection down at the transport layer. And when we say transport layer, we mean the networking TCP/IP stack. We don't necessarily mean TCP specifically. So we're just talking the network protocols at this point. So maybe there are weak algorithms, or there's a usage of expired or invalid certificates that's allowed, which means we could come up with our own phony certificates. Maybe this allows the launcher or the attacker to launch man-in-the-middle or phishing attacks. Or there are vulnerabilities that will reveal user data, or there's potential account theft. So we're talking the thing, and really up to HTTP, that gets the data up to the web app. Anything down in that or down below in the network. Improper error handling, we've discussed this already in several locations. If I can I can send something bogus to the server in the hopes that it will give me back more information than I should have, including tables and databases, directory structures, things that will help me craft my next attack. So it might even give me a knowledge of the source code. So we can, as an attacker, take advantage of things like default accounts and logic flaws. So we use information and error messages to help identify further places to attack or vulnerabilities. So the information could be network timeouts, system call failures, null pointer exceptions, databases not available, app environment problems, web app logic flow. Any one of these might return information that helps us attack farther. Maybe the developer is not storing things cryptographically properly. Maybe they developed an app that does not adequately encrypt their code or securely store sensitive data. So therefore, since there's insufficient cryptography or something that's easily broken, we can go ahead and steal and modify the data, regardless of the weak cryptographic storage. Maybe there will be broken authentication or broken session management issues. So the attacker impersonates a user by exploiting vulnerabilities in how the authentication works or how the session is managed, which, by the way, that cookie stealing and token thing, that's session management. So types of broken authentication, broken session management, you put your session ID in a URL for everybody to read. Or we exploit timeout values or passwords. We can also have unvalidated redirects and forwards. So I install malware, and like we've said before, the user is forwarded or redirected to a malicious site. They put in their username and password, thus bypassing access control because they're giving the username and password to us, which we then forward back to the legitimate site, and now we have a copy. Or we have them log into us, and then we redirect them, and they log into the legitimate site. The user won't realize that there's something wrong with logging in twice. So attacks on web services, there are so many attack vectors, and there will be new ones as web services evolve. They're going to be based on XML protocols that are vulnerable to web app threats. So the attacker can attack the web service at the presentation layer, security layer, discovery layer, access layer, transport layer. Like we saw, there's a whole pyramid of possibilities. So those are some common additional web app attack types.